Hey everyone, welcome back, and let's write some more neat code today. So today let's solve diameter of a binary tree. So we're given a binary tree. All we need to do is compute the length of the diameter of the tree. And what exactly is the diameter? It is the length of the longest path between any two nodes in a tree. And this path may or may not pass through the root, so it doesn't have to necessarily pass through the root. So let's look at an example. So given this tree, the diameter of it is 3. Why is it 3? Because you take a look at the path from this 4 all the way to this 3, and that runs from the root 1, right? So you go left 2 and you go right by 1, right? 2, 1, 2 plus 1 is 3. So that path is 3. That's the diameter. Now, it's the longest path, pretty obviously from looking at the picture, but what are a couple other diameters that aren't necessarily the max? Well, look at this. If you go to its left, that's a path of 1. Go to its right, that's a path of 1. So the diameter from here is going to be 2. And what about this? If you look at, the left and right are null, so the diameter from that is actually 0. Same for this 5. The diameter running through this is 0. The diameter running through this is 0. And technically, this is also a possible solution because the diameter through there is also 3, right? You go here 1, you go here 2. So what would be a brute force way to solve this problem? Well, let's take every single node and consider it as, let's say, the topmost node in that diameter. So let's find what's the max diameter from here, from this node 1. Well, we want to go as far down right as we possibly can. We want to find the lowest node on the right side. Well, we see this is null, right? So the path on the right side is going to be 0. That's the maximum on the right side. What about the left side? Well, we go down to a 2. That's good, right? We went down 1 node, and we can either go down 3 or 4, right? So basically now what we're doing is recursively finding the diameter from this spot, right? So clearly we can see a little bit of repeated work that we can possibly cut down on. But let's continue the example from here. What's the biggest diameter we could find? Well, we obviously see that both of these paths will lead down to the same level, right? The lowest node could be on this side or on this side, so it doesn't really matter. But what is the length of it? Well, from here, the length is 2, right? And to go from this 1 down to this 2 is also another 1. So in total, this entire side is length 3, right? So we take 3 plus 0 and find that the biggest diameter we could find running through this 1, through this root node, is 3, right? But is that the biggest possible diameter we could find? It's actually not. Right? Let's take this 2, for instance, right? We want to find the lowest node on the right side, right? Clearly, we go down to this 4, then we go down to this 6. So the lowest node is 2 edges long. What about the left side? The exact same thing, right? The 5 is 2 edges away. This is 1 edge. This is another edge. So now we can take 2 plus 2 and find that the diameter running through this node is actually 4. That's bigger than what was running through the root, which was 3, right? So this is our biggest so far. And if we were doing the brute force, we'd probably have to do the same thing through every node, right? From this 3, we'd find, okay, this is 0, this is 1. So then in total, the diameter from here is just 1. And the diameter from here, since both left and right subtrees are 0, the diameter through here is going to be 0. And similarly from here, the diameter running through here is going to be 1. Diameter running through here is going to be 0. But you can see that that was kind of a lot of repeated work, right? First, we had to find the lowest from here. Then we had to do the same from here, right? So can we do this a little bit? If we do this in a recursive way, we can actually eliminate the repeated work. What we started was top down. We started from here, and then we wanted to find the diameter from here. But really what we can do is start from the bottom recursively, right? So find the diameter of these 2 nodes first, right? And I'm just going to kind of visualize it a little bit. It'll probably make more sense in the code. So the brute force way that we did it is technically big O of n squared, where n is the number of nodes in the tree. I'm going to show you how to do it just big O of n. where we only have to visit every single node at most one time. So basically what we're going to do is we want the diameter running through here, right? We're going to have a max variable, right? We'll call it max. Initially, it's going to be 0, right? So we want what the max diameter is running through here. Okay, to do that, let's first solve the subproblem. What's the max diameter running through the right subtree? Well, clearly it's an empty subtree, so it's just going to be 0, right? Okay, now let's find the max running through the left subtree. Okay, that's great, but now to do that, we have to also find the max running through 3. So clearly we're just visiting every node once so far, right? So let's find the max diameter through 3. Okay, let's look at its right subtree. That's 0, right? Because it's empty. And now let's find the max diameter through the left subtree for 5, right? So then we're going to look at its left and right subtrees, which are both empty, right? So the diameter through these two trees is 0. So then what's the diameter through this tree? Well, in reality, we can tell it's 0, right? But now when we go back up to here, what are we going to do? In reality, we don't just want the diameter through this, right? We also want the height of the tree starting at 5, and we can tell that that as well is 0, right? And this part might be a little confusing. It'll make more sense in the code, but basically for each of the nodes in here, we want the diameter and we want the height of the tree. So the diameter through here is 0 and the height is also 0. So then we want to find the diameter and the height for 3, right? So first of all, how can we find the height of the tree starting from 3? Well, we want to look at its left subtree and its right subtree, right? Find the height of the max of these, right? So basically the max height from left and right, the max height from these, right? And add 1 to it. The reason we're adding 1 is, see, there's an extra edge here, right? So clearly the max of this is 0 and the max of this is also 0, but basically for convention, notice how this is a null tree. In reality, by convention, we say that the height of a null tree is going to be -1 because the height of a tree with a single node is considered 0, right? And this just helps the math to work out. So I'm going to leave a -1 here saying that the height of this tree happens to be -1. So then what's the height from 3? Well, the max of left and right is going to be 0, right? So 1 plus 0 means 1, right? So we can put a 1 here for the height of the 3. Well, what's the diameter of the tree? We can find the diameter by taking the height of the left tree, so left, plus the height of the right tree, which in this case is -1, right? So plus right, and then plus 1 and plus 1. So in reality, plus 2, because for each of these trees, we see there's an edge going to it, right? So this edge, right? And what that's going to do is -1 plus 1, that's going to cancel out, right? This is going to be 0, meaning the height from this part is 0. That makes sense. That kind of shows why we're putting a -1 here for the math to work out. What about the left tree? Well, that's going to evaluate to 1, right? Because the height of this is 0, but we're adding a 1 here for this edge, right? It's kind of getting messy now, but so basically what the diameter of this is going to evaluate to is going to be 1 plus -1 plus 2. That's going to end up being 1. It's going to be 0 plus -1 plus 2, that's going to evaluate to being +1, right? And that makes sense because just looking at this, the diameter is going to be 1, right? Because there's one edge going to its left node, the right tree is empty, the overall diameter running through this is going to be 1, so we're just going to put a 1 over here. And in reality, this is actually pretty simple. Maybe some of the math is making it more complicated than it needs to be. You'll see that the code is actually pretty simple. But the key here is that we're going bottom up. We're finding the diameter from the bottom nodes and then working our way up to the root. That's what's allowing us to cut out some of the repeated work. So you can see that these diameters and heights are actually going to apply to these nodes as well, right? This node is going to have a diameter and height of 0, 0. This node is also going to have a diameter and height of 1, 1. But what about this node? What's the diameter and the height of that node? Oh, and by the way, before we actually do that, remember our max diameter, which we're looking for, is now going to be 1 from over here, right? So we can actually update this and set it to 1 now. So to compute the diameter and height from here, actually all we need to do is take a look at our equations again, right? So this is the equation for the height, the max height. So we look at the max left and right heights first, right? Both of them are going to be 1, right? The height of this is 1, the height of this is 1, right? But we're also adding a 1, so 1 plus the max height of both of those. So in reality, the height from here is going to be 2, which makes sense, right? You take a look at this, that's length 2. This is also length 2. Okay, but what's the diameter, right? That's what's really important. We want the diameter. We're only computing the height because that's what we're going to end up returning to the upper nodes, right? That's the only reason we're computing the heights. The diameter we're computing is to potentially update the result. So let's compute the diameter, right? So how are we going to do that? Clearly from this equation, left height plus right height plus 2. So the left and right heights are both 1, right? So we're going to take 1 plus 1 plus 2, right? That's just our constant. So the diameter we're going to compute is 4, right? That makes sense because take a look at this. That's 2. This is also 2. We add those together. The diameter is 4. So we can actually update our result again, changing it from 1 now to 4, right? We know that's actually going to be the value we end up returning because when you go up to this root node, and let's say we want to compute the diameter and the height from here, or actually let's just compute the diameter because we don't really need to return the height to an upper node, but the diameter from here is going to be the height of the right subtree plus 1. And the height of the left subtree, right? The left subtree is 2. The right subtree is -1. And we also have our constant. Remember, we're adding a 2. So plus 2, that's going to end up being +3. So what we're saying is the diameter through this root node is actually 3, which is not even bigger than our max right now, which is 4. And that does make sense, right? Because when you go here, this path is empty, it's 0, right? So the diameter through there is 0. But take a look at the left, right? This is one edge, this is one edge, and this is another edge, right? So that's a total path of 3, which means the diameter of this is going to be 3. Clearly, we know that our result happens to be 4. And you can also see that we didn't really need to traverse every node more than once. And the main reason is because we're returning the height every time we have a recursive call. If this is really messy to you, I recognize that this is not probably the best explanation I've given, but I think the code is going to make more sense for you. So the first thing we're going to do is have a result variable. This is basically a global variable, right? And the reason this is going to be global is because we're going to have a nested function, depth first search, passing in only one parameter, the node, the root that we're traversing from. And so since this variable is outside of this function, this variable is going to be accessible in here globally. Okay, now the base case for this depth first search is, of course, if the root is null. So what are we going to return? Remember, we're returning the height, right? Now, what's the height of an empty tree, of a null tree? It's not 0 because that's what the height would be for a single node, right? For a null tree, the height is actually -1 because that lets our math work out. And now what we want to do is recursively find the height of the left subtree. So I'm going to run depth first search on root.left. I want to find the height of the left subtree. I also want to find the height of the right subtree. So let's run depth first search on it. So now I want to find the diameter of the current root that we're traversing, right? And I can do that using the left and right heights. And if it's greater than the result, I can update the result. So how do we find the height? We take 2 plus the left and plus the right. And so basically this is going to give us the diameter. So then we can potentially update our result. So we can set the result to the max of itself and what the diameter that we just computed, right? This is the max diameter. So we're potentially updating it, but maybe we're not updating it. And now remember what this function is for. Depth first search, we're trying to return the height. So now I have to return the height running through the root node. What is that going to be? Remember, we wrote it down in the drawing, but it was pretty messy. It's just going to be 1, the constant, plus the max of the left and right heights, right? Because Whatever the height of the max of these is, plus 1 is going to be the height running through the root. And that's actually it. So the picture might have overcomplicated things for you. So what we want to do now is actually call this function, passing in the root, and then we can just return our result. So you can see that this is pretty efficient because this is a linear time algorithm. We're basically traversing over the entire tree, right? You can see that this is basically a regular recursive depth first search function. The only thing we're modifying is we're returning the height, and we're potentially updating the maximum. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon.